This evening we're going to talk about the Dinosaur project here on the Hanson Ranch. And I will give you some of the background, and I will share with you the direction our research has gone and what some of our results are thus far. Before we start, though, I'd like to have prayer. And there are a couple of things I'd like to include in the prayer, both our safety here in this camp out in the middle of nowhere, and also one of our participants last week, James, those of you who know James, is in the hospital right now. They don't know what's wrong, but he's got some serious problem. So we want to remember him in prayer. Let's bow our heads. Loving Father, we thank you that we have the privilege of studying about you through nature. There are many things in nature that confuse and perplex, and in order to understand them right, we need your help. And we invite you to bless us, give us understanding, be here with us tonight as we contemplate this project that's gone on now for 20 years. Father, we also ask for your protection as we are in a tornado watch area right now, that you will be with us here in this camp, and you will cover us with your hand. Also ask for James, Father, that you will guide the doctors in figuring out what's wrong and get him back on his way to health. We love you and we praise you for these things that we ask in Jesus' name. Amen. All right, so what happened to the dinosaurs? That's one of the persistent questions that we seek an answer for here in this project. It's also a question that every one of you has, and some of you have answers, some of you think you have answers, some of you don't have a clue. So we're going to take a look at what we've learned. Let's start by talking about this project and the dinosaurs that we encounter here. In the main quarry areas, mostly we're finding the dinosaur in Monosaurus annectans, the duck-billed dinosaur. It may look innocuous there, but this animal is 30 to 40 feet long. That's big. This building is 48 feet long, so if you had one of these here, he would be filling up 2/3 of the building just with his length. And these are big, big animals. This is what he looks like when we get hold of him. And some of you, all of you, I guess, got to the quarry today or yesterday to see this portion of his tail right here. We also have found over the last year another dinosaur by the name of Anzu wiley. Anzu wiley is a oviraptor. This is somebody's fanciful illustration of what he looks like. Anzu would stand about this tall. That's a big bird, a big dinosaur. Not a bird, but a big dinosaur. And there is an Anzu that they just found, and some of you may have seen this if you follow dinosaurology at all, that is 2 stories high. So that would be even bigger by quite a bit. But the one we have is about 8 feet tall. Here's some of the bones in his body. We found these bones right here, and this bone, and this bone, and this bone, and some of these bones of the ankle just this year. And this is the hallux right here that identified it as Anzu wiley. That was found by Dr. Wood last year. We have a Blisodon, which is a dinosaur that's characterized mostly by teeth. Not very much is known about it. It's kind of a minor player in the whole story of dinosaurs. But Nanotyrannus is not. This is a dinosaur that has gotten us a measure of fame because we found the second one that was ever found. The first one was found many years ago, and it sat around for a long time, and it was finally described by Bob Bacher and another fellow, and they named it as a new taxon, Nanotyrannus. Then we found the second one in 2001. I have no idea why I did that. And then the third one was found by a group from the Burpee Museum in Illinois. And they, not knowing about the work of Bob Bacher, they decided that this was a new taxon, that it was not a new taxon, that it was a new example of a T-Rex that was a juvenile. And one of the interesting things about T-Rex, Tyrannosaurus rex, is that we don't have any juvenile ones. They're all adults. Have you noticed that? You don't go to a museum to see a baby T-Rex. The only T-Rexes you see are adults, fully mature adults. So that's an interesting finding in itself, and it begs the question, why would you only find adult Tyrannosaurus rexes? Any ideas? Yes?
They were so feared they wouldn't be killed as children, so they'd grow up and then die.
So they grew up really fast.
No one would attack them. They were that much.
Okay, so that's one idea. Yes?
They had their size and they were taken care of by their parents until they grew size.
Okay, these ideas are interesting, but really, when it comes right down to speculating, what about the possibility that Tyrannosaurus rex grew up fast, so that the number of juveniles relative to the number of adults was small? That's one explanation that you could give. We don't know if that's true or not, but it certainly is a possibility. So they wanted this to be a juvenile T-Rex because why? They wanted to have a T-Rex in their museum. So they said, no, this isn't a Nanotyrannus. Nanotyrannus is a juvenile T-Rex. So they tried to make Nanotyrannus just to take away its nomenclature and make it just a juvenile T-Rex. But many people, including Bob Bacher and Pete Larson and many others, have said that Nanotyrannus is a taxon in its own right. And we believe that's true. All of the characteristics that we find in this fossil are different from T-Rex, so we're quite certain that it is its own taxon. We'll say more about Nanotyrannus later. Here's what he looks like. And if you come to our museum in Keene, Texas, just a few miles from Dallas, you can see a model of Nanotyrannus and also see the bones that we've gotten. Dromaeosaurs, these are the raptors. Saronitholestes, another one of the raptoroids. Nodosaurus, big lumbering animal, the size of a giant pig, I guess, bigger than a pig. Look at the armor on this animal. It's inch thick or more armor all over his back and his neck, and his head is even solid bone, unlike most dinosaurs. And look at those front feet. Take a look at this animal. What animal are you reminded of? Armadillo, that's right. And what do armadillos do? They dig, that's right. People don't like them. And look at these stout front legs. They look like they're made for digging. Pachycephalosaurus. Pachy means thick, cephalo means head. Thick-headed dinosaur. So if somebody says you're a thick-headed whatever you are, if they call you thick-headed, what they're referring to is not a compliment. And this is not a compliment either, because that head that you see there that makes him look smart, there's nothing in there but solid bone. His brain is about the size of a walnut, and it sits underneath that. We have in our collection at the museum the largest Pachycephalosaurus skull that's ever been found. We don't have the full skull, we just have the frontals and parietals. Struthiomimus. Struthius is the genus of ostrich, and mimus means like. So does that look like an ostrich?
Yes.
Kind of, except it's a dinosaur. How do we know it's a dinosaur, class? Open acetabulum. Open acetabulum is what distinguishes dinosaurs from other creatures, among other things. Thescelosaurus, we didn't know much about that until about 3 years ago when we found one, mostly intact, in Triceratops quarry, Triceratops 2 quarry. Here's what Thescelosaurus looks like. They're sheep-sized dinosaurs that didn't really have much in the way of protection from predation. Triceratops, you can only imagine how big a Triceratops is. They are gigantic, massive animals. And that head that we took out 2 years ago is 7 feet from the back of the frill to the front of the nose. 7 feet. That's just his head. Probably weighed 500 pounds when it was alive. So these animals had to carry a lot of weight on their front end. And so they have these massive legs to be able to do that. Troodon is the smallest dinosaur that we have found. Troodon is fairly common here. We know them from teeth and from a few bones. And we have those bones on display in the museum. Here's what Troodon looks like in the flesh. Notice these bones down here in the bottom of its belly. What are those called, class? Gastralia. Gastralia are not ribs, they are bones that support the gut. So even on a little dinosaur like this, there's a full complement of those. And of course, Tyrannosaurus rex is only found here in the upper Cretaceous, in the upper Cretaceous. And Tyrannosaurus rex is big. And this young lady gives testimony to that. All right, so what are we trying to learn here? We're trying to understand what happened to the dinosaurs. The science of doing that is called taphonomy. Taphonomy is the study of everything that happens to an animal from the time it's alive walking around until it's excavated from the ground. So taphonomists would want to know what killed the dinosaurs, what were they doing when they died, and what happened after they died. Did they sit around and rot, or were they buried? Were they carried off? And then what happened to the bones after they were buried? So that's what we're doing here. So that's why every single bone is important. And we have to register and catalog every single bone. And just this last week, we reached a goal of 20,000 bones that we had taken out of the ground here. And Trinity has helped us with that for many years. What killed the dinosaurs? That's part of the question that we try to ask. What is the most popular theory? Okay, that's the most popular theory, that an asteroid struck the Earth and wiped out the dinosaurs in one fell swoop. That theory is very popular. It was pushed by a scientist who won the Nobel Prize in Physics, and he pushed it to the extent of threatening the lives of people who opposed him. But there are many people that don't think that theory is right, and these people have been pushed into the background. Even though this is supposed to be science, it's not science when you threaten people's lives if they cross you. So there's some interesting kinds of politics going on in dinosaurs. But let's look at some other theories of what killed the dinosaurs. There are lots of them. The Earth got too hot and the dinosaurs all died. The Earth got too cold and the dinosaurs all died. These are all published in the scientific literature. It got too dry on the Earth and the dinosaurs died. Too wet and the dinosaurs died. Too little food, the dinosaurs all died. Too much food, the dinosaurs all died. Poison food, and the dinosaurs all died. And this one I didn't put a picture with, but it's been published in the scientific literature. They died of constipation. And I won't go into any details of that one. Other theories that have been proposed, that have been seriously proposed, are that volcanoes killed the dinosaurs. Volcanic activity destroyed the dinosaurs. And of course, the cartoonists haven't ever been very far behind. When there are this many explanations for what happened, the cartoonists are going to make a heyday out of it. So we see all kinds of cartoons about it. But you know, the one that I like the best is this one. What really happened to the dinosaurs? All right, so now turning back to our project, our taphonomic study of dinosaurs. It was begun in 1996 as a cooperative research project of Earth History Research Center, Southwestern Adventist University, and the Hansen Research Station, which is this entity that we're in right here today. We work out here every June, and if you ever want to come for a whole month, you can do that. If you're a junior in high school, you can take a college class that's 4 hours and get credit for it. We are in Niobrara County right here. This is Niobrara County. Niobrara County has the distinction of being here it is up here in the Powder River Basin. Niobrara County has the distinction of being the least populated county in the least populated state in the United States. So if you say it just like that, it's true. There are many more cows in Niobrara County than there are people. Here is our field station from the air. And this is June of 2015. I think at least one or two of you might be in there. This is the way it looked from the air last year. No, this was 2 years ago, I think. And as you're finding out, Wyoming is an amazing place. WS doesn't just stand for Wyoming, it also stands for windy, doesn't it? And weather is another one. The weather here is amazing in its intensity and complexity. Here's some of the views of the area. Here's a tornado we saw a few years ago from our dig site. Some of the beautiful scenery. What's missing from the landscape? Trees, that's right. No trees here. This is a picture that was taken by Ivan Snyder 2 or 3 years ago, I guess. And it really was beautiful. And we didn't just move so we could see it over the camp. It actually was there. No, of course we did. These are some of the directors of the project. And here's where we work. This is the area where we're excavating the main quarry. Right here is North Quarry. This is South Quarry. And over here is Stair Quarry and Teague Quarry and Southeast Quarry. Not Stair Quarry, Teague Quarry and Southeast Quarry. To get here, you walk a mile from there. That's our camp. Here's the dig area over here. And it's about a mile. Just about, I measured 1.2 miles. And it's a nice walk. Those of you who've walked it have discovered. What's that?
The quarry is the mile walk.
Yeah, your quarry, here's North Quarry right there, and Southeast Quarry is right over there.
This was taken back whenever it wasn't there.
When what?
When the Southeast Quarry.
Yeah, it hadn't started yet.
Okay.
Here you can see why we're digging out here. This is what happened when we went around with our GPS and just mapped the places where we saw bones. And you can see there are bones all through this area. This is a quarry, this is a quarry, this is a quarry, this is a quarry. And you can see where the quarries are, but the distribution of bones is all over the place. Yes?
What is the difference between the green dots and the red dots?
Those are different quarries.
Okay.
All right, what's it like to be in the quarry? I don't have to explain that to you because you've all been there, but I want to explain the GPS technology. This is the base station. You see that on the hill up there when you go out to the quarries. This base station reads the same satellites that your cell phone does and all the other GPS equipment. But we have told this GPS station where it is on the Earth. So we let it run for a long time, and we compared its values with values that were taken in various places in Wyoming, and we determined its position within a centimeter or so, and that's its position. So we tell it exactly where it is. So when it takes a reading at the other end, here's the rover, when the rover comes around and takes a reading, that reading is reading the same satellites that the base is, but it reads here on the satellite, on the antenna, the radio antenna, it reads a correction from the base. So the base over here is not only reading those satellites, but since it knows where it is, it calculates maybe the satellites say it's over here or over here, and it says, I know where I am, so there's a 3-foot error there. So it makes that correction, and then it transmits it over the radio here all over the dig site. And this is the antenna here that picks up that signal. So it makes a correction to the data here for this bone. And here's how accurate it is. This is a 1 centimeter square. You know how big a centimeter is? That big, 1/4 of an inch approximately. And there are 10 points inside that 1/4 of an inch. The average error is plus or minus 2 millimeters or 3 millimeters or 6 millimeters in the vertical. So the errors are very small. So we determine our position accurately within a few millimeters. So when we find a bone in the ground, we bring in the GPS, we take some points. Those points go directly into the computer without any error on our parts. And then we take a picture of the bone and we extract the bone from that picture. And then we orient that to those points and lock it in there. And now that bone is a georeferenced position. It now knows where it is in the computer, exactly where it lay in the ground. That means we can put in all the other bones around it and reconstruct the quarry without the dirt there. Isn't that amazing? We were the ones that developed this technology. When we would go to scientific meetings and present papers where we showed these pictures, people would gasp because they've never seen anything like this. And every scientist I know wants to see what the bone's like without the dirt there. And we were showing them this little Christian college down in Texas. So here's an example. This is quarry number 1. And that's the main quarry. This is in 1999. These are the bones that we put in manually. And then from then on, it's all done with GPS. Here's 2000, 2001, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And at the end of the summer, hopefully, I'll have 17 done. And it will look even bigger. So there it is. This is what the bones look like. If you just stripped away all the dirt and left the bones there, this is what you would see. Here's just to show you that quarry is not unique. This is South Quarry. Some of you may have worked over there today. And this is what South Quarry looks like. And not one to leave the worst quarry for our visitors, we saved the best for Trinity. And there's what your quarry looks like. This is Southeast Quarry, and this is Teague Quarry here. And you can see the intensity, the number of bones that are in that quarry is immense. So many bones that it's really hard to work there in a sense. And then there's the quarry that we're working this year called Stair Quarry, way off here with number 5. That was the quarry that we found the Nanotyrannus in. Look how far away it is from the main quarry over here over to here. And in Stair Quarry, we found a whole bunch of Nanotyrannus bones. And you can see them all circled there. And now we're digging down below that in this area right here, looking to see if we can find some more Nanotyrannus. Here's what Nanotyrannus looks like. This is a skull. Here is the maxillary. That's the upper jaw of Nanotyrannus that we found in 2007 maybe. And this is interesting. This is something that Sabrina, some of you know Sabrina now? You know who Sabrina is? This is what she does with the bones. When they've all been cleaned and prepared, they're put on a table and we make 360-degree pictures. And you can take any of those bones and rotate them 360 degrees. You can zoom in on them and do all kinds of things with them. And that's largely her work. So that's the maxillary. Here is the dentary. That's the lower jaw, which also has some of the teeth still in it. It doesn't look very much like a T-Rex jaw. This is the Triceratops we took out over there in that Triceratops quarry back in 2014. And you can see we've excavated all the way around it. We have to get it up on a pedestal just like you do. and then we cast it, and we try to get it out of there in one piece. Here's one of the horns. Here's Mr. Gray measuring the distance between the horns. And there's Carolina, just giving a reference for size. And here is the skull cast up, and I think that's me lying underneath it there, trying to get some plaster on the lower side. Look how big that cast is. That probably weighed close to 1,000 pounds by the time we had it all cast up. I know it had nearly 500 pounds of plaster on it, and we plastered it to a pallet so that we could get it out and handle it. Yes?
So that was orientated upside down?
It was upside down, yeah.
Okay.
Here is the Triceratops after we got it back to the lab. It doesn't have its nose on it. Its nose is a separate piece that comes out this far, but from here to here is 7 feet. And that skull still weighs upward of 500 pounds is my guess. Here you can see the quarry with the Triceratops in place. And look at this little pile of bones over there. You know what that one is? That's the Thescelosaurus. Thescelosaurus that we took out in 2015. And over here are the bones of the Oviraptor, right there and there and there and there and there, and one of them over here and a couple over here. So you can see there's kind of a line here of Oviraptor bones. We hadn't found the duckbill dinosaur yet. These are some of the vertebrae of the Thescelosaurus. Here is the Thescelosaurus in the ground. You can see here's his spinal cord. This is his sacrum here between the legs that holds up the rest of the animal. These are some ribs and some other bones.
That's a very concentrated pile of bones.
Very concentrated. All right, so how do you explain the fact that we don't have dinosaurs today? If you ask a scientist who is a evolutionist, he'll tell you, well, dinosaurs were crossing a river during flood stage. Some of them drowned and they got carried downstream, and they came to rest in a bend in the river, and that's where these bones accumulated. Year after year this happened, maybe as the animals were migrating or something, and so over a period of time, this massive bone bed with thousands or tens of thousands of animals accumulated. But is that what the data say? Let's take a look at the data. Bones lack current orientation. We don't really see the evidence of a fluvial current, a river current. So that doesn't sound like a river. Most are disarticulated, and the horizontal distribution is random. We would expect that if these animals carcasses had been carried downstream in the river and had been lodged in a bend in the river, we'd find carcasses. But we don't find carcasses. We find disarticulated bones. And here you can see the horizontal distribution. And by the way, this is one of the other advantages in doing the GPS work on the bones. I can show you just the ribs, which I've done here, or I can show you any other bones that you want to see. The bones occur in a normally graded bed with some sorting by bone type, but a graded bed is very significant. Let me show you what a graded bed is. This is the bottom 2 decimeters. That's this much of the bone bed. Bottom 2 decimeters, this is in South Quarry, has big bones. The next 2 decimeters, they're smaller. Can you see that? Next 2 decimeters, they're smaller. Next 2 decimeters, they're smaller yet. So each time you go up 2 decimeters, you find smaller bones. That's a graded bed. Big bones at the bottom, little bones at the top. The only way you could get a graded bed is if all the bones were transported as a single catastrophic event. So what we have here is not a process of dinosaurs being killed crossing a river over thousands of years, but we have a single catastrophic emplacement of bones so that they're in a graded bed from big bones at the bottom to little bones at the top. That's a very different scenario from the other one. The bones are well preserved. They weren't exposed to weathering. Here are some of the beautiful bones we've taken out. The conservative estimate is 5,000 animals buried in the bone bed. That's a lot of animals. Here is, just to show you what that means, here is just a little section of all the bone bed. Notice the bone bed extends over a wide area here. We're just going to take this square and blow it up. And here you can see that square. And the part that's not yet excavated is in black. And the part that's already washed away is in red. And yellow is where there's overburden. So now if we take away all the overburden, and then we paint the area we haven't excavated yet with the bones that we are finding in the quarries, it would look like this. That's what we have left to do. So if any of you are interested in a career in paleontology, here's a good opportunity for you to study dinosaurs, and there are plenty of them to go around. How do we know how many dinosaurs were there? Well, we take the number of bones in the body, we take the number in our catalog, we divide it, and we find out how many animals that represents, and then we relate that to the amount of excavation we've done, and we get a number of dinosaurs per square meter. And the value we get for 1 meter squared is about 1/10 of a Monosaurus. So that means if you sit down in one of the quarries and start excavating and take 1 square meter down to the bone bed, you'll find 1/10 of a dinosaur, of a 20th to 1/10 of a dinosaur. We estimate the original extent of the bone bed is more than 50 hectares, indicating there may have been as many as 10,000 to as many as 25,000 animals in the original deposit. Yes?
What is a hectare?
It's a metric acre. We also look at the little things. Here are the screen washing of the sediments around the bones, and we get all kinds of stuff out of that. For scale, this is 1.5 millimeters across. 1.5 millimeters. That's actually the head of a pin. And these bones have been glued to the head of the pin. And these are some shark teeth, some little claws from probably a reptile of some sort. Here's some fish teeth, some crocodile teeth, alligator teeth, some sharks and skates and ray teeth. This is a troodon tooth. Remember the little dinosaur troodon? These are shark's teeth here. This is a shark's teeth. This is a dermal denticle. Dermal denticles are the bone that grows inside the shark's skin. And that's why back in the old days they used to use shark skin as sandpaper, because of these bony plates that were in the skin. And then these are some mammal teeth down here. We find lots of plants, leaf imprints, coalified wood, petrified wood. Watch for amber. Amber is beautiful yellow, orange color and clear. If you see that, we collect it and we're saving it because you can do pollen analysis on amber. We can find out what kinds of plants they were. We also have prints of palm trunks and palm fronds and other things. These are pollen grains that came from South Quarry. We just took a piece of dirt out of the wall and processed it for pollen grains, and these are some of the grains we found. Some of these are very easy to recognize. This is a bisacate grain, as is this one down here, and this one. Those are coming from a pine-type tree. These are from ferns. These are plants we don't have anymore. This is tilia, the basswood. This is hickory. So we can, this is jugulans, the walnut. So we can identify some of these kinds of plants that we see there. This one's very interesting. This is an acritarch. Acritarchs grow in marine sediments. And so that seems to indicate that we are dealing with a marine setting. Yes?
So what's the process that takes the amber and so you can find all these?
How would we get the pollen grains out of amber? We'd have to dissolve the amber and then separate, just wash it until it was all gone. And then we would take the residue and process it for pollen. Typically what's done in sediments is you take the sediment, you dissolve it in concentrated hydrofluoric acid, that takes out all the silica, and then you dissolve it in concentrated hydrochloric acid, takes out all the carbonates, and you probably do that in the opposite order. And then you treat it with potassium permanganate and sulfuric acid, and that oxidizes away all the sediments, all the other material in there, and it leaves just the pollen grains. They're almost impossible to destroy. They're very, very tough. They're made of a waxy substance called sporopollenin. Yes?
But do you have this palynology research just from amber, or you have from the sediments as well?
No, this came out of the sediments. We have not done amber yet. We still find some bivalves, uniotype bivalves, which are fresh or brackish water, and also some gastropods. Yes?
Have you ever found like blood in an amber?
No. No mosquitoes, no blood, no DNA. But that doesn't mean it's not there. We just haven't found it. Okay, so let's just skip that one. The graded bone bed, that's best explained in deep water. Rapid deposition in deep water. There are a lot of other characteristics here we could talk about, but this is the model we have proposed. These animals had to die and rot somewhere. So they had to die and then sit around and rot. They could have floated, bloat and float, we call it in taphonomy. They could have floated out here in this ocean and then been washed up on the shoreline. And when they got up on the shoreline, there were animals waiting with nothing to eat there, the theropod dinosaurs. So they came in and chomped on those rotten carcasses and ate what they could out of them. That may have been enough to kill them too. But there were still theropods around. And then all of a sudden there was another catastrophic earthquake, and all of these sediments that contained all those bones were remobilized and transported out and deposited in deep water offshore. And that made a graded bed. That's how the big bones got on the bottom and the littler bones on top, in a debris flow, subaqueous debris flow. So here we have a study to try to find out what happened to the dinosaurs. And we're learning a lot about it by studying these bones out here in the quarries, and you have a part in that. All of you do, but the Trinity group that's been coming for I don't know how many years, lots of years, they have a part in this. And your work is going to contribute to this ongoing research to try to understand what happened. The interesting thing about dinosaurs is nobody's upset if you say there was a catastrophe that killed the dinosaurs. Isn't that interesting? Everybody thinks it was a catastrophe. They just don't want it to be the flood. They want it to be something else. But it could have been the flood. And having our eyes open to alternative explanations is always a good thing in science.